All right, we're just going to wait a few minutes to let everyone settle in, and then we'll start in a few minutes.
All right, so it looks like the chat is working. Perfect.
Yay.
So before we get started, everyone can just make sure to, make sure they have pencil and paper because we'll be going over a lot of problems. We'll start very soon, as we get more people.
Yes, exactly 3:05. So.
Okay, should we get started?
Yeah.
It seems like we're basically ready to start. Welcome, everyone. I know a lot of you are probably coming from the grades 8 to 12 section, but if you're not, we'll just start out with some intros, some fun polls, just to kind of try to get to know each other, and then we'll begin with the math content. So just to start, I'm Michael. I'm a rising senior at Trinity. Besides math, of course, I love debate and journalism as my other main interests. And the thing I love most about math, I guess, is the community that I often see at the competitions or in classes.
Hi everyone, I'm Foyez. I'm also a rising senior at the Trinity School. Aside from math, I really like chemistry and biomedicine. And I think my favorite field of mathematics is game theory and combinatorics. Yeah, and I think just my favorite part about math is, I think same with Michael, the community and just solving problems together in a collaborative spirit.
Hi, I'm Maia Posternack. I am a rising junior at Trinity School. Beyond math, I really like computer science and art. And as they both said, I really like the community and I'm really passionate about encouraging other people to love math as much as I do.
Yeah, hey everyone, I'm Akash. I'm a rising senior at the Trinity School. I think like everyone else here, I think this entire club has a great passion for trying to spread that love of math to everyone. One of the reasons why we're doing this camp. So we're super psyched about that. Outside of math, say my passions are computer science. I like that a lot, as well as chess. I play that too.
All right. So I'll screen share again and we'll start our lesson today.
Before that, perhaps we could release some of the polls. Maya, do you have that function?
Oh, yeah. So we wanted to do some icebreakers with you, just like a regular camp, even though sadly we can't see you, just so you know. We're in a webinar form, so we can't see or hear you. You can just chat or Q&A. So we thought to just get to know each other a little bit, we'd do some fun polls. So I'm going to do our first intro poll. It should pop up on your screen, and you can fill it out when you would like.
As you can see, some of these are somewhat serious. Some of them are definitely not. So feel free to have fun with it. I don't see this issue in the chat, but in our previous session a couple hours ago, some people said they couldn't vote or having issues pressing the submit button. We found that for most people, they just didn't answer all the questions first. So just make sure you fill out all 6 questions, and then there should be a submit button which you can press.
We'll give you like 30 more seconds to submit, and then we'll end the poll and see everyone's results. All right, I'm ending the poll right now. So if you need to do it really quickly. We just have a couple people left. All right. Wow, we're mainly East Coast. Oh, I didn't show results. There.
So pretty similar results from our previous session. A lot of East Coast and Canada, of course. Some from Asia in the early hours. Let's see.
Yeah, is it like 3 a.m. around that there? That's crazy.
It's 3 a.m. in most countries in Asia.
Wow.
Yeah, I got to give a shout out to those people. That's a commitment.
Yeah.
Just so you guys do know, there will be recordings. So they'll be on our YouTube channel. Feel free to subscribe to that. And we'll be posting all recordings of sessions from both 8 through 12 and 5 through 8 every day on the YouTube channel.
Yeah,
So,
let me just do that quickly so you guys have access to that.
Okay. I think Michael's going to be posting some links.
Yeah. And our age limits for these programs are pretty arbitrary. They're just what we think my 5th through 8th grader or 8th through 12th grader might enjoy. But if you're finding this too easy or the other program too hard, you can totally switch between the two, or maybe even skip through the other recording tonight just to see if that was interesting. We do different topics every day, so maybe one day one program is harder for you and the next day it might be easier. It'll definitely fluctuate. So let's start reading.
All right, so I'm going down the ice cream. So chocolate 1. That's interesting. Lion King.
My favorite.
Chopsticks also won last time, which is interesting.
Right, stand mixer is obviously amazing because you don't have to do anything. Like if you're making cookies, it will literally make them for you. You just put in the ingredients.
I think it might have been a more appropriate poll to put who knows what a stand mixer is.
It's
maybe we can do that tomorrow. We see a lot of algebra. That was similar to the last one.
Interesting.
Our group tends to like algebra, so I think you'll enjoy that. And seems 100% of you said that you love math. So you're in the right place.
It's almost as if we didn't give an option to not love math. All right, so welcome to the first day of TrinMathCamp ever. Wow. Today we're going to be talking about methods of a proof, and two pretty simple methods in comparison to other ones are induction and proof by contradiction. And so proofs, if you haven't done them before, which would totally, I'm guessing a lot of you haven't, are basically a way of explaining step by step why you know something is true and saying it so that anyone that reads your proof will believe you 100%, this is true, I can see it because they did the math to do it. And so induction and contradiction are two formats to basically write this proof now, convince everyone that you are always right. So we wanted to start with just talking about logistics, keep you in the know so you know all the programs and everything that's going to be going on. We're going to have 2 sessions a day. You probably read about this in an email sent to either you or your parents. And there's one for grades 5 to 8, which is the one you're in now. And it's from 3 to 5 p.m. Eastern time. And there's one from grades 8 to 12. That will be at 1 to 3 Eastern time. And these programs, once again, if you are younger and want to be than 5th grade and want to be in this program and it isn't too difficult, go right ahead. If this program is too hard, maybe it will be easier later today. If this program is too easy, you can go to do the 8 to 12 session.
Yeah, for sure. As Maia's saying, there's full flexibility with what session you choose. Yeah. And because we're offering the recordings on YouTube, feel free tonight, if you have the time, to take a brief look at both sessions if you weren't able to make it to one, and just see, what might be the right pick for you tomorrow. And each day the recordings will be available for the session. So you're always going to have access to all the sessions for both classes. So feel free to spend as much time as you'd like diving into either.
And just to add to that, there's also, as Maya was alluding to the difficulty, there's definitely a range when we get into, after the concepts we talk about the problems, definitely a range of difficulty. So even if you struggle a little bit with some of the later problems, even just understanding the first few would be great, especially if you're just starting out with these topics.
For sure. For example, tomorrow we'll be learning about Pythagorean's theorem. And I know some of you might never have even seen that before. I know I didn't see it till probably the end of 6th grade or early 7th grade. And some of you might be really familiar with it. So we'll be starting by introducing it and then going on to more somewhat complicated things. But we hope that you'll be able to understand them by the end of the session. And so each day we will talk about a new topic, and then we'll talk about problems for it. And then we'll give you homework, which is suggested. It's not required. We can't really check that you did it, but if you want to have the best possible experience, we suggest that you definitely spend time on it. But sometimes we'll have a lot of problems, so if you feel like you're spending a really long time, more than a couple hours, then you should definitely you can definitely stop. You don't have to spend your entire afternoon on this homework. And then every day we'll be talking about a different topic. Today we're going to be talking about induction and proof by contradiction. Tomorrow we talk about Pythag, And then in future days, we'll be talking about counting, probability, and symmetry in game theory, which is something really interesting because it has to do with economics. A couple other logistic things are that in the Q&A, even if it says it's anonymous, we can see who says everything. So please don't troll. We will kick you out. We're trying to foster like a good learning environment. And then once again, there'll be recordings on YouTube to help with homework. Even if you've been to this session live, we really suggest that you go and maybe click through the recording just to help you with the homework. Like you can go to a similar question that might be on the homework and see how we explain it. So a couple other things we want to talk about before we start are some mathematical notations. And these you probably haven't seen before, but they're like abbreviations for us to refer to stuff without writing them out in like the whole English form. And if you have any questions about it, you can totally ask in the Q&A. We will have people responding. And yeah, so we'll just tell you the different notations that we might refer to. The first is this n, and n is a set of all natural numbers. Natural numbers are all the positive integers, which means whole numbers. So anything from like 1, or it could be 1,000, it could be any positive whole number with like no fraction on it. The next one is z, which is all integers. And integers are all the natural numbers and then all the negative numbers. So once again, a whole number, no fraction, but basically any number within that. Next, we have q, that's all rational numbers. And rational numbers are numbers that can be expressed as p over q, where p and q are both co-prime integers. In short, it just means it's any number that doesn't go on forever. Like it's not the square root of 2 or pi or something, but you could have like 1 and 3/9 or 2/3, not 3/9. But yeah. R is the set of all real numbers. These can all be shown on the number line, and that's basically any number you can think of unless it includes the square root of -1 in general, which we probably won't be talking about a lot, and you probably don't learn until like 8th grade or so. So if you're not at that level, it's probably any number that you can think of. The floor function basically is the closest integer below a number. So if k is a number expressed as a decimal, then the floor of k is the greatest integer less than k. For example, the floor of 2.5 is 2, like 3.1 is 3, 4.9 is 4. It's the lowest integer near that number. And the ceiling function is the opposite of that. It's the closest integer above that number. So if k is a number expressed as a decimal, then the ceiling of k is the greatest integer more than k. For example, the ceiling of 2.5 is 3, 3.1 is 4. It's not necessarily rounding, it's just like the closest thing, either above or below. Finally, we're going to talk about exponents. So for any integer k, that when you write k to the n, this means that you multiply k by itself n times. For example, 2 to the 3rd, or more conventionally, 2 cubed, is 2 times 2 times 2, which is 8. You probably, even if you haven't used exponents before, you've probably seen this in the form like squared, like 2 squared is 4. So yeah, so we thought just for a little hot quiz type thing, just to see if you understand this, and if not, we can explain more. We'll just set a poll, and we'll have different numbers, and you'll say like what set of numbers it's in. Where are we? Okay. All right, so here's a poll. I'm gonna leave the kind of cheat sheet up, but if you want a challenge, maybe don't look at it. 1709 is where our school, the Trinity School, was founded, so we have some fun references in there. Once again, if you can't press submit, it's probably because you didn't answer all the questions. That's what we've seen in the past. So maybe try to make sure that you answered all the questions, and then it should work. Yes, for number 2, we only offered one answer. So that might be a hint that it only works in one of those. Well, more specifically, it works in 2, but if you want to like think of what it's most likely.
Is only one answer available for 2?
Yeah.
Oh, I'm sorry. That's an error on my part. Just put one of the ones that works, I guess, in that case. Apologies for that.
You don't need a calculator.
Go ahead. Yeah.
For today, just make sure you have pencil and paper because we'll be going over a lot of problems. So just make sure you have a place to work with.
All right, I'm going to give you like another minute and a half, and then I'll be turning off the poll. So just make sure to have that submitted by then. Of course, you can take notes if you want. We will also be posting this recording, though, as I said before, on YouTube, so you can view it at any time, forever. If you want to see as soon as it's posted, we highly suggest subscribing to our YouTube channel. Michael put it in the chat earlier, just in like the beginning of the lesson.
Again, yeah.
But you'll also get an email with all this information later. All right, like 30 more seconds and then I'm closing the poll. If you don't know something, guess. You won't be penalized at all. We are not even checking who's saying what. So we're just for fun. All right, I'm gonna end the poll now.
Okay, so it seems we had some confusion with some of the problems. So, for number 1, a lot of people got that it was that 729 is part of the natural numbers. Just make sure to also note that if the way we ordered it, if something is part of n, then it's definitely part of z, q, and r. Just going from a smaller subset to the larger sets. So if anything is n, then it's also z, q, and r. So for 1709. Obviously, it's a natural number, it's a positive integer. So then necessarily it would also be an integer and a rational number and a real number. So just make sure you understand that as we move forward. For number 2, I know that Akash noted that unfortunately we only put one answer, but as a lot of people noted, the right answer is both Q and R. Well, because it's Q, it is also R. So just make sure you guys understand that smallest is n, and then n is within z, which is within q, which is within r. Third question. Yeah, so just make sure you remember, just logically that floor is the bottom and then ceiling is the top. So we're taking the floor of 10.6 and we'll round down to 10. And if it was the ceiling of 10.6, then we would be looking at 11. Seems that most people got the floor of pi. Ceiling of 19 divided by 7. Yeah, so just making sure, a lot of you selected either 2 or the actual quotient. So just make sure when we're talking about ceiling, we're thinking about rounding up. So 19 divided by 7 is 2 point something. Round that up, we get 3. Yeah.
And also just to add to Michael's description of the sets we're working with, what he said, I really do want to underscore that they're all, not only are they increasing in size, but they're actually subsets to each other. So an example that you might have seen before is that thing, with the square and the rectangle, how every square is also a rectangle, but not every rectangle is also a square. So you can kind of think of that like the natural numbers and the integers. So every natural number is also an integer. So 5, that's also an integer. However, you take an integer like -2, that's not a natural number. So the order that we've listed it here, N, Z, Q, and R, that's kind of like the order of size and of subsets to think about.
Okay. So now we'll get into proofs. All right, so let's talk about proof by induction. A proof by induction asserts that statements P1, P2, P3 are true given that a base case, P1 is true, and an inductive step, Pn is true, then Pn plus 1 is true. And this may sound very confusing at the moment. I'm gonna read you the next slide and then we'll go back and talk about more what this means. All right, so the proof by induction is kind of like a domino effect. One can think of induction as knocking down a rally of dominoes. You begin by pushing the first domino, and then the first domino pushes the second pushes the third pushes the fourth, and so on. This is exactly how induction works. We push the first domino by proving the base case, and then the inductive step, assuming true for n and proving for n plus 1, is the rest of the domino effect. So to add on to this, when we do a base case, we're going to find the smallest number that we're trying to prove it works for in like the set of all numbers. So let's say we're trying to prove that something is true for everything from n, which equals 0, to like something giant, like thousands. It's normally probably like infinity, but we don't really talk about infinity in proofs as much. So we first, for the base case, we'll just plug in 1 to our equation because n equals 1, and that's the smallest possible number we're trying to prove for. And then the inductive step basically says, okay, if it's true for 1, prove that it's true for n plus 1. And if we're able to make a logical step that proves it's true for 2 or n plus 1, then we know it's true for 2, which means the inductive step that if it's true for n, then it's true for n plus 1 works to prove that if it's true for 2, it's true for 3, and so on, until just by these two things, a base case and the inductive step, you've proved that it's true from every number, from like 1 to infinity.
Yeah, so it seems like we don't have any questions about it now, but of course, you all, if you have any questions, feel free to ask them in the Q&A. We're more than ready to answer them. But yeah, I think, Maia covered super well. And even if you have any issues understanding that for now, I think it'll become very clear once we actually get into the problems. So without further ado, yeah, why don't we go forward since we don't have many questions?
Yeah. I think we'll do 1 or 2 problems and we'll discuss them, then you'll try to work on them by yourself, and then we'll explain them, and then we'll have about a 10-minute break before we come back. So the first problem is prove that for every number from 1 to n, where n is any number ever, if you add them all up, it equals n times n plus 1 over 2. So maybe first think about your base case, the smallest possible number we're trying to prove for. What would that be? And then for the inductive step, we can assume it's true for n, and we just want to prove it's true for n plus 1. So maybe change this equation, which says it's true for n, and try to do something to both sides of it to prove that it also is true for n plus 1. So you want to turn this equation into something that says the exact same thing, but for n plus 1. I'm going to give you a couple minutes to try to work on that, and then we'll come back together and we'll explain it. And if this one's confusing, don't worry. If this is the first time you ever saw induction, I know I was like super confused when I first saw induction, but after you see an explanation or two, you kind of get the hang of it because it becomes kind of logical.
Maia, do we have a poll for this problem?
I don't think we have a poll for this problem. I can check though.
So I see a question in the chat, what is n? So essentially, we're trying to show that this equality holds for all positive integers n.
Yeah, we should have specified that actually.
Yeah.
That's our fault. And if it was like the perfect math equation, it would say for all positive integers n, where n is anything 1 or greater.
The way you can all start thinking about it is like, let's say n equals 4, right? 1 plus 2 plus 3 plus 4, that gets us 10, right? And then let's check the right-hand side of the equation. We plug in n equals 4. 4 times 5 divided by 2 is 20, divided by 2 is 10, right? That's a way to check that that it works, and that's what we'll get into with induction. That's the base case in this situation. Then we'll give you guys a little bit more time to think about how we can, if we assume that it's true for n, we can prove it for n plus 1. But yeah, just have some time to think about that.
So I see a question about the 3 dots. Just to clarify, the ... basically means kind of, it's lazy notation for basically fill in the pattern. So really what the left-hand side is just saying is just take the first n positive integers and then just add them. So as Michael said, he stopped at n equals 4, so that'd be 1 plus 2 plus 3 plus 4. If you stopped at 6, let's say, it would be 1 plus 2 plus 3 plus 4 plus 5 plus 6. So the ... is like, you can't really write that out n times. So the ... is just trying to let you know of that's the pattern we're dealing with.
Right, we'll give you about 2 more minutes until 3:35 Eastern time, and then we'll talk about it. And once again, if you didn't get it by then, don't worry at all.
Someone's asking if we can just go back to the definition slide for briefly.
Of course. The definition of induction.
Yeah.
If n equals 1, then you would just stop at 1. So you wouldn't have to say like 1 plus 1. You just say, you don't have to add it to anything. You just say 1 for the person that asked that question. P is just saying like a random number in a set. So it's just our like fancy way of denoting like P is the first number that we're trying to prove for. And then P of n is the nth number we're trying to prove for. If what it said in the equation that we show later was more P1 we just basically could call 1, and Pn we can call n. We're just writing fancily. Yeah, so I'm gonna, now that you saw this definition, I'm gonna go back to the question slide and then start explaining it in a minute. All right, so I'm gonna begin. I always mess up. So our base case, we're gonna do for n equals 1, and this is because the smallest integer greater than or equal to 1 is 1, and we're trying to prove for everything bigger. And so for the domino effect to work for all the integers, we wanna start at the smallest possible one, and then it will work for everything else. So for n equals 1, we have that 1, so we don't have to go all the way to like 1 plus 2 plus 3 because n only equals 1, equals 1 times 1 plus 1 over 2. which we can see equals 1. So the base case works, which is great. And then let's talk about the inductive step. So for an inductive step, we assume it works for n. In this case, we just renamed n to k because it's more conventional, but totally use n. I normally use n when I'm writing it. But we can assume that for some k, you add up all the numbers from 1 to k, and that equals k times k plus 1 plus 1. Then we want to prove that it works for k plus 1. So we're going to add up all the numbers from 1 to k plus 1 and make that equal to k plus 1 times k plus 2 over 2. If that makes sense, because it's just the exact same thing, but it's just for k plus 1. So what we're going to want to do is make this first equation, add something or do something to both sides that make it still equal. So we'll probably have to add the same thing to both sides and make it into the equation we really want. So what we did here is we added k plus 1 to both sides. So that this side right here works perfectly. It's every number from 1 to k plus 1 added up. We're all good. And then this side right here says k times k plus 1 over 2 plus k plus 1. And we want to prove that this equals k plus 1 times k plus 2 over 2. A cool thing we can do about this is we can see this statement and we can see, oh, actually that's like saying k over 2 times k plus 1. And we can see this statement and say, oh, that's like saying 1 times k plus 1. And so if we see k over 2 times k plus 1 times k plus 1, we can factor that out and we can say k plus 1 times k over 2 plus 1. And what's really cool is that's the exact same thing as saying k plus 1 times k plus 2 over 2, because just by simplifying it out. And here we have the text on the sides that in really formal proofs, it's how you say, this is what I'm doing, I want you to know what I'm doing. Instead of me explaining it out to you, this is a way of explaining it. And then finally, we say, so we are done at the bottom. And this is a really fancy thing for proofs. We normally want to say something at the end that are like, we got it, you're good, you don't have to read anymore. So we can say it like this, so we are done. We can also put like a square to show that we're done. Or we can write QED, which means like quid eras demonstratum or something, which basically means like everything we wanted to say has been said. So I'm going to give you a couple minutes to like absorb this and read it yourself and try to understand truly how it works, and we'll also answer some questions.
Yeah, I know, you know, a lot of people are understanding it, but if you're still having some issues understanding, you know, perhaps looking at it from a math perspective, I think the domino example is still very useful. So what Akash put into the chat was, you know, basically with the domino effect for this problem, you know, I think we can all see how for n equals 1 or for n equals 2, it's pretty easy to see, right? Like, you know, if you have n equals 2, 1 plus 2 is 3. Then you, on the right-hand side, 2 times 3 over 2 is also 3. So we have that base case, right? That's, you can kind of imagine that as like the first domino falling. Now, in the situation where we're trying to prove a statement that's completely wrong, you can imagine that when the first domino falls, instead of all the dominoes falling, you know, maybe that first domino doesn't even knock down the next domino because it's a false statement. However, if it's a true statement, what's going to happen is that once the first domino falls, right? If we assume that one domino falls, and we can prove that the next domino must fall if this domino falls, then as soon as we know that the first domino is going to fall, then to infinity, we know that all those dominoes must fall, right? And so transitioning from like, you know, that logical stuff back to math, here what we did, as Maya said, here we looked at n equals k, right? We looked at, let's assume that for some k, this equation is true, right? Now, if we're assuming that's true, we can add k plus 1 to both sides because this problem is about summing the first, you know, k or k plus 1 integers. So it just makes sense for us to try adding k plus 1 to both sides, right? Because now on the left-hand side, we're getting what this equation would be if it were to be the first k plus 1 integers. And on the right side, our goal is to show that now that we've added k plus 1 to the previous right-hand side, we're trying to show that ultimately through some algebraic manipulation, or just simply put, like changing around some stuff, we can get to what the right-hand side should be, or what we're expecting it should be if the equation were to be true. And you can see here that ultimately we're getting to k plus 1 times k plus 2 over 2, which as you can see is the same thing as n times n plus 1 over 2. So, right, so we were able to show that assuming that some domino falls, we were able to prove that the next domino must fall, right? And as soon as we were able to show that, you know, the first domino in the series of infinite dominoes falls, now we show that every single domino falls. So that's basically what induction is a really powerful proof for these kind of problems, right? We were able to show that just from really 2 steps, right? Really just saying we have our base case and we have the inductive step. And from that, we were able to prove it for all positive integers. So you guys, if you have if Akash or Maia, do you have anything to add?
Yeah, I realized I didn't explain how this simplifies out to this. It's because k over 2 plus 1 is the same as saying k plus 1 all over 2. K plus 2 all over 2. And then you can multiply that by k plus 1 to get this. Also,
yeah, sorry, go ahead.
I'm sorry. If this is a confusing concept if it's your first time, so we're going to be doing a bunch of problems for you to get it. But if you have any like really specific questions about like the algebra we did, totally put them in. And if you're a little confused, don't worry at all.
Yeah, and just to add to Michael's like conceptual description, I think, you know, something important to note about this domino falling is that we're using a very specific property of the integers that is that the difference between consecutive integers is 1, right? So after 2, you can definitively say that the next integer after that is 3, and then 4, and then 5. So this knocking down a domino actually works. Whereas like for other number systems, it's harder for that to be the case. Like there's not really, like if you say, okay, what's the next biggest fraction after half? That doesn't really exist because there are just so many fractions. But because the integers are always spaced apart by 1, then that domino can always just fall like 1 onto the next integer, onto the next integer. So that's kind of why this domino effect works.
All right, so we're just going to give you 1 minute to write this all down or think about any questions you might have that you might want us to answer when doing the next similar problem, and then we'll go on to the next one.
Maia, the next slide is also about this problem, so maybe we want to go to that because we have a yeah.
For sure, I totally forgot. So this is like a more visual version of the problem we just saw. So let's say you didn't want to do it and explain the problem with all this algebra. You could do it this way. This is also maybe a way that will make the problem make more sense to you. So we can visualize the sum of the first n integers as a staircase. So if like n equals 1 has 1 step, and then n equals 2 is 2, like 2 steps wide. But so here this is like 1, 2, 3, and so each time it increases, and it kind of makes this like diagonal staircase. Or I guess this is the 1 and this is the 2. I was just looking at it upside down. If we duplicate that staircase and place it upside down on top of the original staircase, we can get an n by an n plus 1 rectangle. That's what you can see here. It has a width of n and a height of n plus 1. We only want half the rectangle because we just want one of the staircases, so we can divide it by 2, leaving us with n times n plus 1 over 2. So it's kind of adding every single one of these blocks up, 1 plus 2 plus 3 plus 4 plus 5, to a geometry area problem, making it into this shape and just taking half of the shape. I'll give you a minute to think about it. All right, let's go into the next problem. We want to prove that if we add up every odd number, which can be written as 2n minus 1, so the first one is 2 times 1 minus 1, which is 1. The second is 2 times 2 minus 1, which is 3. And the third is 2 times 3 minus 1, which is 5. If you add them all up, it equals n squared. So once again, we want to think about a base case, which is the smallest possible number out of all the integers that this can happen to. So it might be similar to last time. Plug it in to prove that it works, and then write an inductive step, which will basically say, assume it works for n, and then add some algebra in to make that exact same equation have it for n plus 1. So we want it to be all the numbers up to 2n plus 1, because doing this for like n plus 1, and then if you multiply that by 2 and subtract 1, you'll get 2n plus 1. And we want this side to say n plus 1 squared, or n squared plus 2n plus 1. We'll give you a couple minutes to think about that, and then we'll discuss it. If it's great if you have the answer so far, but we're just going to give a couple minutes for everyone in this call to try to think about it. And then about accessing YouTube, we will put it under like safe for kids. So if you're on that restriction, we'll have it available. Sadly, I don't know if we'll be able to email it because we'll have a 2-hour recording, but we can definitely look into it. Oh, if YouTube doesn't work, right, because you need VPN. We will look into putting it on Google Drive and trying to share it with you. But worst comes to worst, if it doesn't work, it's not going to be like horrible. It would just be to reference for help with homework. We'll really try to look into it though, putting on a Google Drive. I don't think we can email it though because it's going to be 2 hours. It's so great that so many of you are saying that you can do it, but also it's a really difficult concept. So we're just going to give 1 more minute and then we'll talk. All right, I'm going to start explaining. If you didn't finish it yet, don't worry. You can totally go back and finish it after class, and we're hoping the explanation will make it make more sense. All right, so the first we have the problem here. Prove that for every number where you do 2n minus 1, for every number less than n and equal to n, it will equal n squared. So our base case, once again, is where n equals 1, because we want the smallest possible number that this will work for, and it works for 1, which is great. So we just have to add up 1. There's no numbers to add it with it, and it equals 1 squared. So the base case works. Check. Now we want to do the inductive step. And so the inductive step, we want to prove that if it's true for k, then it's true for k plus 1. So once again, we want to change this equation where we know it's true. It's adding up all the numbers until you get to 2n minus 1 or 2k minus 1 and make that equal k squared. And so to make this work for k plus 1, we want to add up all the numbers until we get to 2k plus 1. Because if you break it down, if you want to say 2 times k plus 1, here I can annotate, 2 k plus 1 minus 1 just equals 2k plus 1. And so since we added this on this side, we want to add it on this side, just because you have to add the same thing on both sides to keep the equation true. And then what you can see really cool about here is we can factor it. And some of you might not have seen factoring before. I don't think I saw it till 7th or 8th grade, so totally don't worry if you haven't. But if you have, you might know that k squared plus 2k plus 1 is the exact same thing as saying k plus 1 squared. So it works. We've proved it. And so once again, we put all the text here. So by inductive hypothesis basically means we did our assumption and then we added some stuff to it. And by factoring means we were able to turn k squared plus 2k plus 1 into k plus 1 squared. And as you can see right here, we added our little square, which basically says, you're done, we've proved it, we're all good, you don't have to read anymore, worry anymore. So once again, I'm gonna clear this just so it makes more sense. And I'll answer some questions. We'll give you a couple minutes to digest it. And then we're gonna go on a 10-minute break for you to get some water, walk around, so you're not sitting here for 2 whole hours. Let's look at the questions.
And just to add to what Maya said, I think this first step is really important. So I'll just describe in one more way. So I think what we're really doing why we're saying this left-hand side is equal to this right-hand side. Oh, I guess, sorry, you can't really see my cursor. I'll start drawing. So why this part is equal to, we said it's equal to k squared. And we just substituted in k squared. And the reason that we could do that is because we assumed it's true for n equals k. So if we assume it's true for n equals k, then what we're essentially using is this statement. And if you look at this statement versus what we have here, it's exactly the same thing, just with k. So we take these, we use the fact that we're assuming this, we just take it for a fact that it's true. We plug in k squared. And then what ended up happening, which is a little bit algebra as we've been doing, is that we get k plus 1 squared. Which is, if we put in a 1 here, that's what we would get. Anyway, I just wanted to reiterate that part because it'll be very important for the problems that we do later.
2k is not 2000. I see that question. It just, instead of saying n, we said k because it's fancy. But no, we're just saying k is any number ever. Other questions is, if you're lost, once again, don't worry. This is something I learned in like 9th grade. So if you're younger than that, which I'm assuming you are, it's kind of insane that you're learning it. And we're gonna do some more problems to try to help you get it. And tomorrow's a totally different topic. It's Pythagorean's theorem. And personally for me, I find it a lot easier than this. So don't worry at all. I can't see the rest of the Q&A, Akash, because I'm sharing the screen. But if you see any really interesting questions to share with everyone that aren't like case specific.
Sure. There's one question about k squared, but that was a few minutes ago, so I think we addressed that.
The question about the colon right here is just like a punctuation mark. It just means we're doing it for n equals 1, and this is the answer. And yeah, we'll be talking about Pythagorean triples tomorrow, after we've talked about what Pythagorean theorem is.
Yeah, so I'm sure a lot of you know the Pythagorean theorem, and I'm sure a lot of you don't. So I think what'll be great about tomorrow is that, we'll first establish some ground on what the theorem is, and then there's actually a lot of interesting stuff just beyond what the theorem is, different ways to prove it, different ways we can apply it. So I think it'll be a good topic for everyone.
And I think I mentioned this beginning, we cannot see or hear you at all. There's no way we can. And if you want to talk to us, either do it through chat or Q&A. That's the only way we can really communicate. And we just did that, so in case someone that isn't supposed to be on this call gets on, we don't want them to be like disrupted because of like Zoom bombing and stuff. All right, I'm going to explain the question about the domino effect again, and then we're going to go on. If you already understand this, like, just don't listen to me for a second, and then we'll talk later. It's like a domino effect, basically, because we say, okay, we know it's true for 1 when n equals 1. Here's how. We're going to do the algebra and show you it's true for 1. Then, with the inductive step, we're going to say, okay, if it's true for one number, prove that it's true for the one that's 1 higher. So if it's true for 1, prove it's true for 2. If you prove it's true for 2, then you know it's true for 3. If it's true for 3, you know it's true for 4, etc. And so that's how it's a domino effect. If we know the inductive step that says if it's true for n, it's true for n plus 1, and we know it's true for the first number, then we know we can say if it's true for 1, it's true for 2, it's true for 2, it's true for 3, forever, until we get every number ever. So it's kind of like a domino where you push the first one by saying that you know it works for 1, and then like the action of kind of pushing is like, oh, if it's true for 1, it's true for 2, etc. And it kind of like goes down the chain. All right, so right now we're going to give you a little break because 2 hours to sit in one place is a lot. So please be back by the computer by 4:10 Eastern Standard Time, so exactly 10 minutes from now. And we will be starting then. So we don't know if you're back by the computer, so we're just going to assume so. We can't really check or wait for you. So just please be back in exactly 10 minutes. You can walk around. If you have questions, we can be answering some questions now as well.
Maia, do you want to keep screen sharing or should we switch?
Should we switch? That would be smart. Yes.
All right.
Do we stay in the meeting? Yes. We'll be back talking really soon.
Maia, can you just enable screen sharing?
Oh, so yes, totally sorry.
Yep.
If the way to use proving methods to solve problems is very simply if it asks you to prove it. Like many problems you don't have to really prove it, but in like competitions sometimes, or in like a lot of the math summer camps that we're kind of doing currently, we're doing our own more advanced ones, it will definitely come up. If it is confusing, don't worry at all. Really confusing for me too. And I've said this before, but every day is a different topic. So we're going to do some more problems, try to help you get it. If you have a very specific question beyond like, this is confusing, we'll totally try to understand it and explain it to you.
Hey, Maia, I just want to check. Is it still recording?
I believe it's still recording, yes.
All right, cool.
The n equals k thing is just, instead of saying n, we're just saying k. We're just giving a different letter. The schedule, I don't know if Akash is saying it. I don't know if he's on the screen right now, but basically, it's today, every day from Monday to Friday, from 1 to 3, we're going to be having a more advanced problem solving session for 8th to 12th graders. And then from 3 to 5, we'll be having a session that's more for beginners. For 5th to 8th graders, these kind of restrictions for age are really arbitrary. You can do whatever you want, and we'll be posting all the sessions online afterwards for everyone who wasn't able to make it live, and for you to rewatch while you're doing homework. You can also check out the harder session right now, or when it's on YouTube, to see if that makes more sense. We're talking about different topics every day in different sessions. So today we talked about the pigeonhole principle, which basically says if there's n pigeons and or n holes and like less than n pigeons, and there has to be more than one pigeon in every hole if they were like flying holes, which was kind of fun. Yeah. So to answer your question, or Alia, the reason why we choose a different letter is just because it's conventional. It doesn't matter at all. It doesn't change any of the math at all. It's just because if you want to be really fancy while writing a problem, you do it. In the proof for problem 1, I'm going to pull it up right now. I don't think Akash is by his computer. I think he's taking a walk too. So you're not going to be able to see it, but I can see it. The proof for problem 1, basically, sorry, I'm getting to it. We had k times k plus 1 over 2 plus k plus 1. We said that k times k plus 1 over 2 equals k over 2 times k plus 1, and then k plus 1 equals 1 times k plus 1. So we were able to factor that into k plus 1 times k over 2 plus 1. And then we were able to say k over 2 plus 1 is the same as saying k plus 2 over 2. And we were able to combine those terms to say k plus 1 times k plus 2 over 2. So n does not equal any number. Something that's a really hard concept to get, so if you don't get it first, is n is a variable that is just saying you can plug any number into this. Right now we're talking about integers. So n could be 5, n could be 1,000,000, n could be 1,000,000 then 2. Who knows? So the point of these proofs is to say that if it's true for n, it's true for n plus 1. So it can talk about any number ever without actually saying what the number is, which is really cool because we're just using algebra. I'm going to go to the Q&A. You will probably not be learning proofs in 6th grade. I honestly learned them in like 9th grade out of school, which is kind of cool because you're learning something that you won't be learning in school, which means you can be like smarter than everyone at your school, which I find really cool. So yeah, that's the answer to that question. The proof shown on the screen right now is what we're going to be talking about afterwards. So you'll have to wait and see more about it. Homework every class. We will have a homework for you tomorrow. It is suggested, it's not required, and you shouldn't spend way too much time on it. Like, don't freak yourself out over it. And if it's too hard, don't worry. We will also have a forum for questions about the homework, and we will be answering questions about the homework in the beginning of tomorrow's class.
I'll say especially for today, I believe the homework is quite long. So it's really just a collection of problems. So definitely don't feel the need to solve every problem Some of them can be quite hard. So I would just, glance at them, try to solve a couple if you get the chance. But we just want to stress that there's no pressure about the homework or completing the homework at all.
Yeah, like if you want to do the homework, just maybe set a time limit, like a timer for an hour, and be like, I'm not going to go over this hour, just so you don't stress yourself out about it, really. And then we'll have the recordings posted while you do your homework. So you can go to any point in this recording, you can go to me saying this right now and see if a question that you're having doing homework might have been answered during class. If you have homework and you don't understand, maybe just read the problems and maybe rewatch some parts of the video. And if you can't do it, don't worry. We're going to be discussing answers tomorrow for the more complicated ones, and we're going to be going on a whole different topic tomorrow. So if you don't really understand it that much, it's not going to really affect you negatively later. I'm seeing what is the ... again. ... just is our lazy way of saying, okay, from every number from 2 to the 0 to 2 to the n. So in here, if n is 5, it's saying 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3 plus 2 to the 4 plus 2 to the 5. All right, we're going to be starting again in 1 minute. Yes, Ryan, n can be any number. It's just saying, it's like having an equation with a variable, but there isn't something that it has to be. This class will end by 5. We'll try to end it 5 minutes early. So for sure, don't worry. All right. You guys have 1 minute. Just your 1 minute warning. Akash, could you go to the first session really quickly? The first question really quickly. Some people are having questions about it.
Yeah. Problem 1?
Yes, problem 1.
And
I got you.
Right here.
There you go. Maybe go to the proof just so that they can see the whole thing for
Yep.
1 minute, and then we'll talk again. The homework will be via email. We'll send you an email with a link to the YouTube video and a link to the presentation and a link to the homework. So you'll be all caught up.
Michael sent the link to the YouTube channel, correct?
He did, but we can also email out the link to the video.
Yeah, for sure.
Tonight. But yeah, if you look in the chat, there should definitely be the link to the YouTube channel, probably twice in there. You suggest you subscribe, might be easier. Makes us feel cool. We're ooh, we're YouTubers now with our 50 subscribers. Yeah. So do we want to start up again, Akash?
Yeah. All right, I'm just. I found the link, so I just copy and paste it into the chat again.
Perfect. And a PSA, we have a lot of people on this call, so we don't really have time to check everyone's proof, but I'm sure you're on the right track. But if you're sending us all the proofs, we don't really have time to check it. We're sorry. We have a couple of volunteers trying to answer questions, but we might not be able to get to yours.
All right. So Maia, do you think we need to give any time for this problem yet, or if people thought about it already?
I just went on it as soon as I said to go on the break, so I don't know if they thought of it.
Okay, so why don't we think about it for a little bit, and then we can get going on it. There's a poll midway to the solution, which I think should be helpful.
We're not talking yet, so don't worry if you can't hear anything. We're giving time to read this problem and try to work it out yourself through induction.
All right, Maya, do you think we can start the first part?
Sure.
All right. So the first part, of course, is the base case. So we're going to plug in n equals 0. That's kind of the smallest case we're looking at here. So when you plug in n equals 0, you get 2 to the 0. So I understand this might be a little bit weird if this is your first time seeing exponents, but it's a basically common rule that anything to the 0th power, except for 0, that's a little bit weird, but more or less anything to the 0th power is 1. So 2 to the 0 is 1. And then this is also equal to 2 to the 1 minus 1, which is great because this is exactly what we wanted to show, because we're saying that if you go up to n, then it should be 2 to the n plus 1 minus 1. So here n is 0. So we have n is 0 on this side, and on this side we have 2 to the 1 minus 1. So the base case works. Now the harder step is the inductive step. So as before, we assume that the statement is true for k, and then now the goal is to prove for k plus 1. So we actually have n here. I think as Maya said, k or n is really fine. They're almost interchangeable when you're doing the proofs. But anyway, so we have written out what we're dealing with. So we plug in n plus 1 on the left-hand side here. So we have this expression. And when you plug in n plus 1, you just get that extra term, the 2 to the n plus 1. Now, there's some question marks on the right-hand side. So we have a poll ready, and we just want to know what do you guys think that we're trying to show the left-hand side is. So as usual, we're going to use some algebraic manipulation, do some stuff, factor. But at the end of the day, after all our steps, it's important to keep in mind, what are we actually trying to do here? So Maya, I don't know if maybe you could start up that poll for problem 3. And then, let's see, can I start the poll? Hey, yeah, so start the poll for problem 3, and we'll just get some input as to what people think we're hoping the right-hand side should be. My advice would be to look at the right-hand side of the problem statement, and then think about the fact that we're trying to prove it for n plus 1. So think about what adding 1 to the right-hand side means here. another way of thinking about it is whenever you see an n, just plug in an n plus 1. So if you take the right-hand side and plug in n plus 1, that'll give you some insight as to what we're trying to do. All right, so it seems we're about halfway, so let's wait for a few more people to get their votes in.
All right, I'm ending the poll now in like a couple seconds. So the people that haven't voted yet, please vote really quickly. And just guess once again. If you want to guess, totally guess. If you don't want to respond, you don't have to either. It's great that people are starting to understand it. And once again, if you don't, it doesn't matter. We're going to be learning about, I think, stuff easier tomorrow. All right, I'm going to end the poll now.
All right. So you definitely have a lot of different answers, but it seems like the vast majority got the question right. So yeah, what we want the right-hand side to be is 2 to the n plus 2 minus 1. So maybe I'll just explain why that's right. So if you look at the right-hand side, let me just get on annotate. Yes, if you look at the right-hand side, it's 2 to the n plus 1 minus 1. So if you think about plugging in n plus 1 instead of n, what you're going to have is 2. So I'm just going to replace n with n plus 1. And then that plus 1 is still left over. And then, of course, the minus 1 is also there. And then if we simplify this, oh, sorry, I guess I just didn't write that one. Then if we simplify this exponent part, n plus 1 is just n plus 2. So then we have 2 to the n plus 2 minus 1. So, so yeah, a lot of you are correct. That's exactly what we're trying to do here. So maybe now we can show how to close this out. I'll just clear the annotations. All right. So we start out with this sum here. Then, just like we did in the other examples, we focus on the first n terms. So we take these first n terms, and then we use the fact that we're assuming it's true for n. So we're assuming it's true for n. So what we can do is that we can use this property, the property that we're actually trying to prove. So we can use this. And then we just substitute. So we take 2 to the 0 plus 2 to the 1 all the way up to 2 to the n, and we substitute it for what we have here. And we get this because from there. So once we have this equality, this is really the most important equality. And then from there, it's really just algebra. So generally speaking, you typically imply the inductive hypothesis. So that's just a fancy term for using the fact that we're assuming it's true for n, some sort of substitution. And then now is some algebra. So we see that we have two terms that are 2 to the n plus 1. We have 1 here and 2 there. So we factor the 2. And the minus 1 is still left over. And then 2 times 2 to the n plus 1 is just 2 to the n plus 2. If you think about exponents, this is just multiplying 2 n plus 1 times. And if we multiply it by 2 another time, then we're multiplying 2 n plus 2 times. And that's exactly what 2 to the n plus 2 is, if you remember how we defined exponents. And then this is exactly what we wanted to prove, as you guys said in the poll. So that means we're done. All right, so are there any questions? Just gonna check the chat in Q&A. Feel free to submit anything in either way. Someone said they put k as the variable, which is completely fine. N or k are both good.
Yeah, we've done K in the past, and then we kind of switched it on you. So
Yeah,
we
sorry
were
about
probably
that.
confusing on that part.
You can essentially read k and n as being almost synonymous in this case. Someone asked what we're doing tomorrow. We will be doing the Pythagorean theorem. So we'll be discussing what it is and then also some cool applications of it and getting a little bit deeper into it.
So we've been getting a good amount of feedback that today was pretty hard, and we're going to definitely carry that into tomorrow and making it simpler.
Yeah, today is definitely a more difficult day, especially if this is your first time doing proofs. And then even within proofs, induction is a hard method. So it's definitely very useful, and I'm sure you'll see it later on. This is definitely on the harder side of what we'll be doing. Tomorrow will definitely be more laid back. So with the Pythag theorem, I'm sure some of you have seen it. And if not, not only is it more simple, but it's also quite visual. So I think that will also help.
Mm-hmm. And it's just like one rule, like one formula that you just use to apply
Right.
to a bunch of problems.
All right, Maia, unless you're seeing anything, maybe you should go on to the next induction one, and then we'll go on to some contradiction.
Sure, yes.
All right. So before we go on, I think it's worth just noting a general kind of method that we're beginning to notice here. So first off, I'm sure we've all seen this now. There are two steps to induction, right? The base case, which in the domino analogy is kind of knocking down that first domino, and then the inductive step, which is mathematically speaking, is assuming n is true, proving for n plus 1. In our domino analogy, it's just verifying that knocking down one domino really does reach the next domino and gets that domino effect. So the base case, typically that's the easier part of the problem. So that's you just plug in n equals 0. It's not always n equals 0, by the way, but it normally is either n equals 0 or 1. Just plug in like kind of your smallest case. and then just check that both sides are equal. So that's just a little bit of arithmetic. The inductive step can be a little bit challenging because it's not so straightforward. So here's just kind of a general outline to how to approach the inductive step. So first, you're going to write out the expression for n plus 1. So maybe just to go back so you have something to reference, what I mean by writing out for n plus 1, I just mean literally just writing this out. So you're typically going to have some sort of like addition series maybe. So you're just going to go up to n and then add that n plus 1th term. So going back to, so that's writing out for n plus 1. Then substituting the first n terms using the inductive hypothesis. So that sounds fancy. Really what it means is just what I've trying to show is the most kind of important part of this step, which is just taking the first n terms and replacing it, in this case, with 2 to the n plus 1 minus 1. But more generally speaking, you're just using the fact that you assume true for n equals k, which is up here. It's essentially just a problem statement. And lastly, basically the last thing you're going to do is just move the terms around a little, maybe factor, simplify some things. You have to be a little bit clever, but it definitely, with practice, these things just make much more sense. But you just have to end up showing that what you have is actually equal to what you want it to be. You have to show that it's equal to plugging in n plus 1 to the right-hand side. So here, after some work, we factored some stuff, we remembered what exponents were, and then we managed to prove that it's true for 2 to the n plus 2 minus 1, which is what we wanted. That's kind of the general outline of how these things work. So I guess let's try to apply that to one more induction problem. After this, just as a heads up, we'll be talking about one last method of proof, which hopefully is a little bit easier to grasp. And then we'll do a sample problem there. And then from there, I think we will probably be good. All right, so we'll just give you guys a few minutes to think about how to approach this. Also, I should highlight that unlike some of the other problems, this says odd integers n. So earlier when I talked about how all integers differ by 1, you might want to think about what is the relationship between odd numbers. When you jump from 1 to 3, 3 to 5, 5 to 7, how much are you jumping by?
Akash, you're doing contradiction right now, which is a new type of proof, just to clarify.
We're currently doing one last induction one, then we'll move on to contradiction right after this. All right, maybe so we can fit some contradiction in, we can get started on this one. So let's do the first part. So first, I guess, as always, let's cover the base case. So the first odd positive integer is 1. So we plug in 1 and we get 2 to the 1 plus 1, which is 2 plus 1, which is 3. And 3 is, of course, divisible by 3. So the base case is done. Now for the inductive step, this is a little bit different than what we did before. So normally we, as always, we assume that the statement is true for n. What's different here is that we now have to prove it for n plus 2. This is because we're proving it for odd positive integers n. So I boxed that here. And if you think about kind of odd numbers, 1, then 3, and then I should just use a text box instead. 1, 3, 5, 7, 9, and so on. All these numbers differ by 2. So the key observation is that odd numbers differ by 2. So normally when we're dealing with just integers, each integer differs by 1. 1, 2, 3, 4, you keep going up by 1. For odds, you go up by 2. So that's why we plug n plus 2 into our statement and not just n plus 1. So when we plug in n plus 2, we get 2 to the n plus 2 plus 1. Then we rewrite 1 as 4 minus 3. So we still have our 2 to the n plus 2, but we just write it in a way that'll be a little bit more convenient going forward. Then we can take this 4 and factor it. So 2 to the n plus 2, if you write out 2 being multiplied n plus 2 times, you can just take away 2 of those times, and 2 times 2 is 4. So that's why they're equivalent. And then since these two terms both have a 4, you have 4 times 2 to the n plus 1 minus 3. And then this is actually done because we can observe the following. So 2 to the n plus 1 is divisible by 3 because we assumed it's true for n. We assume that 2 to the n plus 1 is divisible by 3. So that's just by assumption. And 3 is, of course, divisible by 3. So if you have a number that's divisible by 3 minus another number that's divisible by 3, you get another number which is divisible by 3. So you can kind of do some examples in your head to reason this. So for example, if you have 15, which is divisible by 3, and you subtract 6, you get 9, and 9 is also divisible by 3. So that is how you prove it for this one. Maybe we'll just wait for a few questions, and then after this, we're going to head to proof by contradiction. So someone's saying, can we explain the factoring in the second step of the inductive? Yeah. So if I understand you correctly, we're just trying to show that 2 to the n plus 2 is the same thing as 4 times 2 to the n. So maybe I can just draw that out a little bit more explicitly. So 2 to the n plus 2 is the same, that one. Maybe I should stay on the slide. So you have 2 times 2, and then this goes on for a while, right? And in fact, it goes on for a very specific amount. It goes on for n plus 2 times. So I'm trying to draw x's for times, by the way. So 2 to the n plus 2, what it means is you multiply 2 by itself n plus 2 times. So when going from here to there, what we're doing is we pull out 2 of the 2's. So we say that's the same thing as 2 times 2 times the rest of the 2's. And if we pull out 2 of them, there's 2 here, and we had n plus 2 in total, so that leaves us with n here. So if we simplify 2 times 2, that's just 4. And then 2 multiplied by itself n times, if you just remember what exponents are, that's just 2 to the n. So that explains this step. All right, it seems like they get it. Okay, so I think let's move on to contradiction. We can understand that, do a sample problem, and then from there, we will see you guys tomorrow. So let me just flip through to the proof by contradiction part. There's some extra problems which you can maybe think about at a later time. So proof by contradiction. So the way proof by contradiction works is, proofs always want to do, you want to take a statement and show that it's true. That's what a proof is. And the way proof by contradiction works is that you start by assuming the opposite. So you want to show that if something is true, you just take the statement, say the exact opposite, and say, okay, let's think about what are the implications if the exact opposite is true. Then we do some calculations, do some algebra like we did before with the induction, maybe some factoring, and then the goal is to end up at a statement that is obviously false. So if you take a statement and suppose that it's false, but then show that actually ends up just being nonsense. If something cannot be false, that means it has to be true. So basically, instead of directly showing why something is true, you just show why it can't be false. So not being false is equivalent to being true. So that's basically the idea behind proof by contradiction. So a standard example when trying to demonstrate this is proving that root 2 is irrational. So first off, just so we're not a little lost, let's explain what irrational means. So if you remember back from the first few slides when we did mathematical notation, we said that rational numbers are fractions, right? So rational numbers, we call them Q. Well, I'm just saying, I'm gonna write it out. So rational numbers, you can think of them as like fractions, basically. So each fraction can be written as P over Q. That's what fractions are like. And then a couple of key facts to know about our restrictions on P and Q. One is that P and Q are integers. So you don't want to have like 2.2 over 3.3. That doesn't quite make sense. And then also is that P and Q share no common factors. So that's basically getting at how we don't want to say 2 over 4, right? Because then 2 and 4 have a common factor of 2. So it's just convention to just write it in simplest form. You've probably heard the term simplest form before. So if you have something like 2 over 4, just write it as 1 over 2, because 1 over 2 share no common factors other than 1, I guess I should say. All integers share 1, but other than 1. So that's what it means to be irrational. Irrational is basically the exact opposite. So just take all of this and just say irrationals are when you can't do this. So irrational means that you cannot represent it as a fraction. So here we're trying to show that you cannot represent root 2 as a fraction. So another way of saying this, prove that it's irrational, it's the same thing as saying prove that the square root of 2 cannot be represented as a fraction. Now keep in mind that we're using proof by contradiction. So So if we're using proof by contradiction, the way that proof by contradiction always starts is that you assume the opposite. So I guess the first step here is, what is the opposite of this statement? I'll just box it. What is the opposite of this? So you can think about that for a little bit. If you have any ideas, feel free to use the chat. Yeah, so someone said that they are relatively prime, referring to P and Q. So that's just a fancy way of saying no common factors. So you can also say P and Q are relatively prime or co-prime. But in, I guess, English terms, what this means is that they don't share any common factors. Okay, so we're getting some responses for opposite. So yeah, the opposite of prove that root 2 is rational is definitely, I'll just write it out. Annotate. So opposite would be prove that root 2 is rational. So the opposite of irrational is rational. So continuing along this stream of thought, assuming that root 2 is rational, that's what we're going to do here, right? The opposite is that root 2 is rational, and proof by contradiction works by assuming the opposite. So what we're going to assume, square root of 2 is rational. Now, if we remember the previous slide, what we do from here is it's not so formulaic. You kind of have to think about what does this mean? So you've assumed that square root of 2 is rational. What pieces of information can you pick up if you assume that? So what might help is to think about what it means to be rational. All right, so some people are getting pretty far in this proof, but let's try and make sure everyone's on the same page. So I guess the question right now is just, what does it mean for something to be rational? All right. So maybe some people are getting it right. I think some people might be confusing it with integers, so it might help to give some some examples. So some examples of rationals. So first off, yes, integers definitely are rational, right? Because they're a subset. Because you can think of 5 as being a fraction, because it's really the same thing as 5 divided by 1. And here 5 and 1 share no common factors other than 1, and they are integers. So yes, 5 is rational. Yeah, but now people are, I think, getting up more. There are also other things, right? Like a fourth. Things I think you would probably more conventionally call a fraction. Like if you saw 5 on the board, you probably wouldn't say, hey, that's a fraction. But if you saw a fourth, 2/3, it's more conventionally called a fraction. And that's really the more general description. So yeah, I think people are getting that rational just means fraction. So now what we can do is we can write the square root of 2 as a fraction, or in other words, square root of 2 equals P over Q. So now what we're going to do with P and Q, and by the way, do remember that these restrictions do apply. So they can't just be any integers, right? So they have to abide by these rules. So I'm just going to box it around 1 and 2. Those are like the rules of what has to be the case for P and Q. Otherwise, it's not rational. So if we get the square root of 2 equals P over Q, that's the same thing. Squaring both sides is 2 equals P squared over Q squared. And just in case the text is a little bit confusing, I'll just write it out with the marker as well. So P squared over Q squared. Now we're going to multiply both sides by Q squared. So what we have is 2Q squared, right? Because 2 times Q squared is Q squared. And then if we multiply this by Q squared, the Q squared cancels. So we just have P squared. So this is the equation that we're currently at. 2Q squared equals P squared. And again, I always like to stress, what is the goal? What are we actually doing here? You know, sometimes we can get so deep into things we forget what we're actually trying to do. So just to remind you guys, so in a proof by contradiction, we started with assuming the opposite. And now what we're trying to do is find that contradiction. It's called proof by contradiction for a reason. So we're continuing along this stream of thought that root 2 is rational, and we're hoping to find some sort of contradiction. We're hoping to find, end up at some sort of statement that makes us go like, wait a minute, that doesn't make any sense. Our assumption that root 2 is rational has to be wrong, and therefore it is irrational. So now we're trying to think, what is wrong about this equation? What raises eyebrows? Why is this not a possibility? So you're going to keep in mind this equation, and what's also really important are these two restrictions. And just a hint to kind of drive you guys in the right direction, I think some of you guys are getting there, is that think about evenness and oddness, meaning is Q even, is P even? If two things are equal, they both have to be even or they both have to be odd, right? Equality is very strong. They have to be the same in every way possible. So think about evenness and oddness, all right? Some people are, okay, a lot of people are getting it. Just wait a little bit to get everyone on the same page. All right. So I think we're getting there. So I will start to explain. So because there's a 2 on the left-hand side, so I'm just going to write LHS, that means left-hand side. We know that both sides must be even. Right? If you have a factor of 2, that's what it means to be even. So if the left-hand side is even, that means the right-hand side is also even. So that means P squared is even. But if P squared is even, that means P is also even. Or in other words, divisible by 2. So you can check that with some examples. So for example, you know, take 16. 16 is even, that's a square. And then its square root, 4 is also even. So if you have a square, then its square root is also even. And if P is even, then you can actually tell that P squared is divisible by 4. So take any even square. So say, for example, 6 squared, which is 36. 36 is divisible by 4, right? Because it's 4 times 9. So if P squared is even, it has a factor of 2. And since you're squaring it, it actually has at least 2 copies of it too. So it's divisible by 4. So if P squared is divisible by 4, then again, looking at our equation, P squared equals Q squared. So what that means is that 2Q squared is divisible by 4. So we see that we have one factor of 2 from this 2, but we need another factor of 2, right? And the only thing to help it is the Q squared. which means that q squared is even. And by the same logic from before, q is even. But now we have a contradiction. I'm going to give you a big hint in that it relates to rule 2 of being rational, that p and q share no common factors. So can anyone think as to why we have now shown that they do have common factors? So just think about it. If you have any ideas, feel free to put them in the chat or Q&A. All right, some people are starting to get it. We'll just wait a little bit less than a minute, and then we can explain the final part. Perfect. Yeah, exactly. So some people putting in the chat, so I'll just say what other people are saying to everyone. So if we key in on two things we have shown that p is even, and we've also shown that q is even. So if p and q are both even, that means that both p and q are divisible by 2. And this means that they share a common factor of 2. But this is in direct violation with our rule number 2. We said that they can't share any common factors. So we have reached a contradiction. So I know that was a somewhat long path, so I guess I'll just take us through a fast forward of what just happened. We wanted to prove that root 2 is irrational. So because it's proof by contradiction, what we do is we take the opposite statement, which you guys correctly said is root 2 is rational. And what we do is we assume that's true. And we did a whole series of operations with using properties of rational numbers and fractions and p and q. And we eventually show that it's just not possible. Because when we try to go down this route, we end up violating a rule of rationals. So we just can't do it. And when I say can't do it, I'm really saying that our assumption has to be wrong. So because of the contradiction, assumption must be wrong. And if you remember the assumption, it was that root 2 is rational. So that statement, I'll put quotes around it, is wrong. So that means that s squared 2 is irrational is right. And that's exactly what we wanted to show. So that's kind of how the proof by contradiction works. I'll just give maybe 30 seconds or something. If anyone wants to jot this down, take a screenshot of this or whatever. After this, I just want to clear the drawing and display the formal proof that we wrote up. But yeah, this is the walkthrough of how a proof by contradiction typically goes. You take the statement, figure out what the opposite is, assume the opposite is true, and then with some clever stuff, you show that that just cannot be the case. So what do you want it to be? You basically show that the false statement is wrong, so the true statement is right. Anyway, so I'm just going to clear these drawings. I believe we had a proof written up. So I will just display this, this hint 1. And then I'll just display this. This is what I said, just more neatly written up. So if any of you want to take a look at that, screenshot that. This is the last thing we'll do today. So we'll just give people a couple minutes to digest this, and then we can sign off for the day. And of course, submit any questions you have in the Q&A or chat.
All right, so while you wrap up, we just wanted to reiterate that we've gotten a lot of feedback that today was too hard. And so if you don't get it, that's totally fine. There will be problems that might help you get it. You can rewatch this video at any time, but we're going to have a totally different topic tomorrow, and we're going to make sure it's easier. So if you're really frustrated, we totally understand. Don't worry. For homework, you will be sent probably, we were thinking a PDF as well as the slides. The homework's at the end of the slides, but we will also send a PDF, and this will all be an email. And finally, you will be emailed a link to YouTube, or you can view our YouTube channel, which I think Akash or Michael just put in the slide. Just to wrap up, because we have like 2 minutes left. A couple other questions I've received a lot of are, this will be happening 5 days this week. This is the only week this summer it's happening, and we don't know if it will happen again. So we will give a answer sheet for homework, as well as talk about the more difficult problems tomorrow. And for sending the recording of this, it's going to take a little while to like upload because it's 2 hours, but I'm going to start uploading it as soon as this is over.
Yeah, just to wrap up, everyone, thank you so much for showing up to the first day. We hope you all enjoyed the content. As Maya said, this first day, particularly for this session, was a little bit harder than what the other sessions would look like. For example, tomorrow is Pythagorean theorem, which I'm sure a lot more of you are at least familiar with. So tonight, we're going to be sending an email soon with a bunch of links for our YouTube, for the homework, for the slides, and for the feedback form. So if you have any questions about the material today, feel free to ask them in the feedback form, which is completely anonymous. And make sure to give us feedback as well, so we know what to do to improve in the next few days.
Yes. If you find it hard, write it on our form. We have a whole extensive form just for you to say what you thought.
Yeah, also just because the homework was mentioned, again, we said this before, but particularly because this topic was quite hard, definitely take a look at it if you get the chance. But no stress if you either don't get the time to do it or it's a little bit challenging. It's definitely a hard topic. Tomorrow will definitely be much more accessible, visual. So I guess keep that on your radar.
Yeah. All right. Bye.